So good morning. So it's to this last day of the conference, and welcome to the last day of the conference. So basically, we have two speakers this morning, and the first is Staffilani, who's going to speak on the wave turbulence theory for a random multidimensional KdV equation.
Thank you, Alex. So first of all, I wanted to thank the CoPI for being here today and for giving me the opportunity to talk here. And I'm going to present a new work with Binh Tran, who is actually at the conference, so, since he's the expert in this work, and I was kind of playing definitely a supporting role, more than the main role. So he will also help me out in case you guys have questions to answer, because he's definitely much more knowledge than I am on this topic. And also would like to thank the NSF, the Simon Foundation, of course, MIT. You see all the logos there. Okay, so let me give you first the plan of the talk. Of course, I will start with a brief introduction, and by now, with all the many talks that we heard on the topic, maybe this is a bit redundant, but it will set the stage. I will talk about two different approaches in the problem that I will present. I will set up the problem that Binh and I worked on. And then part of this setting has in it an equation for a distribution function. And I will talk a little bit about that and the new, in a way, what we think is a new direction in the problem, the statement of the main result, the remarks on the result. And then since the proof is very long, somehow I will give you just some element of it. Okay, so we have been discussed in this context many times what we mean with migration of the energy from low to high frequency. So I'm going to remind you of that again. So we have a solution U of some dispersive PDE, whether it's KdV or Schrödinger or whatever. And I'm going to think of it as a solution on a compact manifold. In particular, think about the torus of dimension D. And I'm going to look at the solution in the frequency space. So I'm going to look at the Fourier coefficient, and that's the U hat K at time t. Now, we know the solution exists, and we are happy with that. What we want to exist for long times, this we can think of them to be a smooth solution if we want. And what we wanted to understand is whether if I start with an initial profile in the Fourier space, frequency space that looks like in my picture here. So this is at time 0. And what I'm representing is the magnitude of the Fourier coefficient in terms of the K frequency. So if we evolve the solution, the initial data into solution for t much larger than 1, what happens? Do we expect that the bulk of this solution is going to move to large K or not? Of course, this, if there is such a motion from low to high frequency, is very rigid. It would be very rigid because, for example, if you look at the area of the subgraph here, well, that's nothing else than the mass, which is conserved, for example, for the Schrödinger equation, and hence at time 0, but also any other time, that area is going to have to be conserved. And then there is also the conservation of the Hamiltonian that gets into the game. So it's not, if there is a movement, it's going to be a rigid one. So we are interested in understanding whether there is this migration from low to high. Now, one approach is, for example, that of looking at the expression that I wrote here. So this is the sum of all the frequency of this magnitudes of the Fourier coefficient square, and then multiplied by the weight k to the sum power s. Why do we do this? Is because if we expect that there is a migration to high frequency, when we hit with this weight, we should see that contribution to becoming larger as t evolve. And if you think about this, it's nothing else than the HS norm square. So what you're looking is the limit as t goes to infinity of Sobolev norms. So this approach, which I learned from Bourgain very early on in my career, has been very, created quite a lot of interest in the community. And here I divided the contribution, and I'm sorry if I don't cite everybody, but into three bigger approaches. So one is the Pde approach. So this is Bourgain and Cookson, of course. I did some work on it. And then my former student Soinger, Deng and Germain, and then with the I team, Carl and Fau, and I like the result very much of Ani Posador called Vishilia. Now, I also learned, actually, thanks to the weekly seminars that we have in our that we do for our grant, a computational approach by Yulin Pan, and I'm actually, thanks to that, thanks to his talk in our seminar series, we are now working together with him and Bobby Wilson, and then the dynamical system approach. By House and Procesi, for example, Kalosh and Guardia, Berti and Maspero, so there is beautiful work in here as well. So I want to now talk about approach number 2. So this is based on a different perspective and is based on finding an effective equation. And I want to approximate the equation that you have originally, let's say, for example, the Schrödinger equation in various ways, and then you take the limits. Now I put here a quotation mark on limits, taking the limits, because this is a very difficult task if you wanted to do it with all the rigor of mathematics, and that has been, as I will talk about more, in fact, this is the content of the talk, it's really the heart of the matter. And once you're able to take this limit, and it depends in which interval time you can do that, then you get an effective equation, and we're going to call that the wave turbulence. This whole setup is under the wave turbulence theorem. Now, fundamental works on this direction, I just cite here like the big names from the beginning, Perls, Hesselman, Nazarenko, Newell, Zakharov et al., and so on. So I will now consider more for the rest of the talk, this approach number 2. Okay, so let me just repeat things that maybe you have seen during this conference a few times. So I'm gonna call AKT the Fourier the Fourier coefficient of my solution U at time t and a frequency k. Now you start with an initial data. This is gonna be a sequence of AK. And these are usually independent random variables. And then what you're interested on is this function nkt, which is the expectation of the size square of this AK. Then you take limits. Now this is really where the hard work is. Large box limit, weak nonlinearity limit, both of them together with the spatial ratio between the various parameters and so on. And then you would like to obtain, or you obtain an effective equation for the nkt. This is the Kolmogorov-Zakharov equation. Now, let me talk about recent results in this approach. So there has been a series of really great papers, wonderful mathematics that have been put forward in this approach number 2, and which you give the rigorous justification of this taking the limit. These papers have proved the rigorous existence of this limit, and almost for the correct time scale. So I wanted to just mention 2 different groups of approaches, even within this approach number 2, but there are 2 different ways of doing it. The one from Lokarin and Spohn, this is at the statistical equilibrium. So the distribution of the data is done with respect to the invariant measure, which is the Gibbs measure. And then the out of statistical equilibrium, I wanted to mention the work of Fau, Buckmaster, Germain, Hane, and Chatat, Deng, Hane, and Collot, Germain. And I will talk more about these results in a little moment. Okay, so what is our setup? So our setup is as follows. So the equation is kind of a generalized KdV, it's the KP equation. And what entails is, of course, dynamics, there is a derivative with respect to t, then there is the Laplacian, but there is an extra derivative with respect just to the first coordinate, that's what x1 is. So your X is in a periodic, so you're a TD. The T is in R, but the first coordinate of this vector X, I'm going to call X1, and you take an extra derivative. So this is a cubic, third order derivative. And then there is the weak nonlinear part. So you have this parameter lambda, which we're going to take to 0. So lambda is small and is a quadratic nonlinearity. And this is in fact important for the rest of the description that I will give. And then the derivative with respect to x1, just the first coordinate. And of course, there is the initial data. So we are interested on the weak nonlinearity limit here when we take lambda go to 0. And like I said, we are periodic, and let's fix the torus, which is from -1/2 and 1/2. Okay, now we generalize this equation by adding some noise right here. So there is a constant CR in here. Now CR is either 0, could be 0, but if it's not 0, it's going to be always less than the power lambda to the minus some epsilon, where lambda is the parameter we use for the weak nonlinearity part. And of course, this notation here stands for, we use, since it's a noise part, this is in terms of Staffilani product and the convolution as well. And here there is also derivative only with respect to the first coordinate. So in we generalized the equation that I mentioned before just by adding this stochastic piece. Okay, now this problem was inspired, I have said, by recent work of Fau, and this assumption that I made of the noise tells you that that is either small or there is no noise at all, and I will describe what where the two difference comes in a moment. Okay, so we want, of course, derive the wave kinetic equation for this equation. What's the strategy? Well, from really far up in the horizon, what we see is the usual way of doing things, which is we approximate the KP equation by a finite difference scheme and derive a kinetic equation for the discretization. And then the second part will be sending the mesh, which we use for the approximation for the finite difference scheme to 0, and then the lambda to 0. To obtain what we desire, which is the kinetic equation for this equation. So this from a very far up on the horizon, that's the scheme. But now, how do we implement this? And I want to go a little bit.
Can I ask a question? Can I ask a question? Sorry, can you go back to the equation that you just showed? Can I just ask? Is there no damping term to balance the forcing? And what motivates the multiplicative noise rather than the additive noise, rather than adding additive noise?
Okay, so this, as far as I know, so this was, as far as I know, it's from this work, recent work of Fau, and I'm not, so maybe my collaborator can answer this question if he knows, since I was just looking at the equation and I don't know that part.
Yes, so I think the idea of how to add this noise is the noise is acting on the so when we write out the density function of this system, right? So there will be a big system, but the system will depend on the length of the vector and then the angle. So I think the idea of this adding this noise is that it is acting on the angles of this density function. So in some sense, this is in the spirit of the fact that we have an angle which is randomized.
And I'm gonna actually thank you, Bin, for telling me, because in fact I'm gonna write down in a moment the equation for the density function, and you will see that where the noise appears, and where in particular this constant. Okay. This constant will be there. So
thank you.
Okay. All right. So here I am. So here we are, and we're going to discretize. So this is really a slide on the setup. And this is the usual way of discretizing our setting. So D will be a natural number. H will be the size of the mesh. And we're going to let either D go to infinity, which then implies H goes to 0. Okay, so then of course, by doing discretization, you have a definite difference of various function alpha and beta, which represent the Laplacian and represent the derivatives. So this is not really relevant for, I mean, no, it's not relevant, but it's pretty standard. Here, I just underlined the parameters lambdas and the parameter CR, which is going to be relevant. And then what is important maybe to look at for a second is the dispersive relation that this problem has. Remember this, if we look at the continuous case, it has a Laplacian and then derivative with respect to the first coordinate. That's why you see here this sign just with respect to the first coordinate of my frequency, and then this one which corresponds to the Laplacian. And then there is the stochastic term. This omega 0 will appear later on as well. Maybe it's better if I tell you right away what it is. That's just the first component of the vector k. So this is k1. And it is relative to the fact that we take this extra derivative with respect to x1. Okay, so this wk, a sequence of independent real linear processes on the probability space. And this condition is just because we want that to be real. So this is a pretty standard setup. And then from here, once you, so this Xi used to be the solution. We are taking the Fourier transform of that. I'm normalizing with respect to the mesh and with respect to this extra derivative that I have. So I'm going to call that AK. And this is the equation that you can write. And this is the equation you should keep in mind in terms of what happens to the solution if you look at it in the frequency space. Of course, we can gauge this omega k, which is the dispersive relation, and that's a simple way of doing it. It's just by multiplying by e to the I omega t. This is again standards. And then just to make things a little bit more compact, the minus here stands for A, and the plus here stands for excuse me, for the conjugate of A. So we're going to be using these indices -1 and +1 just to indicate whether I'm looking at the solution or at the conjugate of the solution. And when you write, and that will be my sigma. So this sigma is going to be just plus or minus 1, and we'll be keeping track of whether I'm working with the conjugate of a complex number or the complex number itself. And again, this is pretty standard in my, my gauge transformation. And now I'm going to look at the system. Again, this is the system, discretized system for basically the solution. And I replaced just for make things a little bit more compact. This M here is just representing the dispersive relationship. Now, at this point, what you can do is analyze, for example, the dynamics of this infinite dimension system and deduce from that your kinetic wave equation by studying the evolution of this guy. So we take a different approach. And what we do is the following, and this again was inspired in some sense by the recent work of Fau. So we consider so we are looking at the density function, and we're going to be out of equilibrium. So we're not going to be looking at the Gibbs distribution. So we have a Hamiltonian, which of course we can read out in terms of in the frequency space. Of course, there is a piece which comes from the kinetic part and another piece which comes from the potential. I remember there is this lambda here because we are making a small. And introduce the real process that this is B1K, B2K, just we write A, this is the Fourier coefficient if you like, in terms of the real part and the imaginary part. And of course, this B, B1 and B2 can be rewritten as a satisfy a certain equation just because they are in fact the Fourier coefficients of our solution itself. So what we wonder at this point is if we start with an initial density of these variables, random variables, some rho 0, B1, B2, how does this density change or evolves according with the equation that the solution itself satisfies? So instead of concentrating on the evolution of the solution itself, whether in the physical space or the frequency space, we're going to concentrate on the evolution of the density. And when we look at that, well, we can write the system that the density satisfies. And this is a system that it's written in terms of the variables of B1 and B2. So those are the variables I'm looking at. And if you write it down, and I'm going to stress this even further when I change variable, I'm going from these variables to the polar coordinates, if you like. So there is a part which is, okay, first order derivative in B1 and B2. Then there are second order, this is important, derivative in B1 and B2, but the second order is linked to CR. CR is the coefficient in front of the noise. So in other words, if CR is not there, so we don't have any noise, then there is not this second order derivative. And then this other part, which is a first order derivative with the lambda, this, as you can see this, because I put the lambda here, this comes from the nonlinear part. And it's not important for now to know what these functions h, a, okay, and hb, okay are, but they are function explicit actually, b1 and b2, explicit in terms of b1 and b2. So in our work, the analysis of this equation is actually fundamental. So I want to spend like one slide just mention that. So we go, as I said, we're going to change variable. We're going to, this seems to be, I'm not an expert at all in this field, but Bin is, and this seems to be a classical way of doing physics. So you're going to change coordinates in, let's say, polar coordinates. So this is what Bin was talking about before. The C2K is the angle. And this piece in front, so the variable C1K represent instead the radius. So once you transform your equation with these new coordinates, and then things become quite interesting because, and I underline again where the coefficient that comes from the noise is, and the lambda that tells us where the nonlinearity ended up is. So you can see this is an interesting equation for rho, for the density, because CR is not zero, hence we do have the noise, and I guess here is, this is the answer to the question that was asked before. Putting that noise in the multiplicative K, in multiplicative form, allows us to have this term here. And actually, if CR is positive, remember that, but CR is not zero, then there is this dissipation. So you have a second derivative with respect to the angle, and that makes things a lot better. And there is a smoothness in here and a good behavior. And also there is this kind of equations with noise have been studied by Flandoli, for example, and other people. I want to mention this. If CR is zero, then there is no dissipation. So really the equation becomes a transport equation, and this is much harder to study. And I just want to mention the work of Ambrosio et al. So this is somehow, the study of this equation is a kind of a place on its own. And I just want to mention that it's different ways of looking at the problem. Okay, now let me state the main problem, because I guess I don't have that much time to tell you at least how we have the proof. So of course we look at the function fkt, which is the 2-point correlation function. So remember, alpha is just basically we made a little gauging, but it is really the coefficient of the Fourier, the Fourier coefficient of your solution. And so this, okay, now you see here the rho, which is the density, and this rho depends on time, of course, according to the equation I just mentioned before. So the main theorem, which is with Bin Tran, and actually I want to say again, he is certainly the person who's driving this project, says the following: assume we are in the periodic setting and the dimension is greater or equal than 4. We need some higher dimension because we need some integrals to converge. I will not go into these details, but the dimension here at the moment has to be higher. So under suitable assumption, the initial density function. Now we'll talk about suitable in a moment, but let me just finish the statement. If t is a lambda minus 2 tau, where tau just has to be a constant, a parameter less than a certain constant tau 0, but the time is big O lambda to the minus 2. So this is exactly the scaling that one expects, the time scaling that one expects. then when you take the limit as the mesh go to 0 or d goes to infinity, that's equivalent, and then lambda goes to 0, this 2-point correlative function tends to f, we call it f infinity k tau, and that f infinity k tau satisfy a 3-wave kinetic equation precisely. Now, just for people who are expert on this, I'm gonna write in the next slides what this CF infinity is. So here it is. It's what you would expect to be in this for the particular equation we are looking at. And you don't need to go through the details, but just I wanted to put up here because it's exactly what one expects to be. And this W here is it's consistent, it's related to the fact that we have this extra derivative in, so if it doesn't appear obvious to people, just because remember we are looking at an equation that is of KdV type and has a derivative in nonlinearity. Okay, so now I would like to spend a little bit of time just remarking on this theorem. So the first assumption, so let's think about the assumption. This is about small noise. Could be 0, or definitely it's going to be less than lambda to the -1 plus an epsilon. If the noise is present, then the initial density that we can consider is more general. That's because if you remember from the equation of the density function, if there is noise, there is a dissipative terms, and hence the study of that equation is more suitable. If no noise, then it becomes a transport equation, and that's much more complicated. We have an example of a solution for that equation, but the study of that equation needs to be done more consistently. That's the plan we have for the near future. In this result, we reach the expected time scale, which is lambda to the -2. So in the work of Buckmaster and all, and Deng and Hani and Collot Germain, which I know a little bit better because it's closer to the kind of analysis that I'm used to do, the emphasis is put on the solution. So the study of when you do this limit, you really look at the Fourier coefficient of the solution. Here instead, we put the emphasis more on the density function of rho, as inspired, as I mentioned before, by the work of Aoun. Moving on, and just to give you an example, in the case of Collot-Germain, the data is expressed in this way. So this is the initial data, is an initial data that you write for your initial data of the system of the solution itself. And what you fix is the distribution of this random coefficient here, and what you look at is the evolution of the Fourier coefficients. So so this is different than what we do because we put more emphasis on the density function that evolves and tells you what is the density of the whole random part of the solution itself. I just wanted to note that by using the equation for the density function rho and not the equation for u, we don't have all the number theoretical part that it's beautiful, I have to say, in the work, for example, of Buckmaster and all. We can avoid that. Okay, now one can wonder, this might have been a question for you at the end, but I'm gonna preemptively answer it. Can one apply an argument to the Schrödinger equation? Well, possibly, but the study of the equation for the distribution function rho, it's gonna be needed, and we have not considered that. Compared to the work of Lockerin and Spohn, one main difference that I already mentioned before, but I wanted to stress again, is that their work is in the stationary statistical mechanics sense, because they assume that the distribution function is the Gibbs, is given by the Gibbs measure, which is invariant for the equation. They are looking at the Schrödinger equation. We are looking at a different equation. Now, let me talk very briefly, and in fact, I'm checking my time. Yeah, let me talk a little bit about what is the kind of framework that we use for taking these limits that I have been talking about. So the framework is, I will say, built on top of the techniques developed by Erdos, Salhofer, and Yao, and Lucarin and Spon. So these techniques are based on dual expansion and the analysis of the Feynman diagrams. And that's the basic idea that we use, but we have to build on top of that because, and I will mention in a moment, because several reasons, but one of them is the fact that surprisingly enough, but not even so much, the using quadratic nonlinearity is actually worse than using cubic nonlinearity. And so we have to refine the analysis of the Feynman diagrams quite a bit. Now, when we do the Duhamel expansion and we read that out in terms of the Feynman diagrams, we stop on a certain layer. Let's call that M. Of course, this M will depend on lambda, and we have to let this lambda go to 0. When we do that, the number of layers will increase. So let's call M this number of layers. And then once you have all your graphs or your diagrams, then you start taking bounds of these guys. And of course, what you want to see is something that depends on lambda, because you would like a lot of these pieces go to 0. So we're going to get an estimate for each one of this graph, each piece, whenever we stop at this M layer, is of the type lambda to some θ1, which is positive, and then a function in terms of m lambda. Now here I wrote a g of m lambda, but g is explicit for us. I just didn't want to write the complicated expression. It's not really useful at this stage. But this is the kind of estimate that we're going to have. Now, when we let lambda go to 0, this m lambda goes to infinity, and this expression goes to infinity. So in order to have a bunch of pieces go to 0, you want it that θ1 is large enough. And so there's going to be the size of θ1 is going to be important, and that will depend on the type of graph you are examining at each step. Now, we have to classify graphs. As a first step, the classification comes in two different partition in two different classes. One class we call graphs that are pairing, and another another class graphs that are non-pairing. And it turns out that the graphs that are non-pairing have the θ1 large enough so that when you take the limit, and this is totally in quotation mark, just for you to have an idea of what I'm talking about, when we take the limit as lambda goes to 0 of the pieces that come from non-pairing graphs, that goes to 0. So that will not be part of the effective equation that we get at the end. So then once we identify this class of pairing graph, well, then that needs a much more refined classification. And I'm gonna say right here that in order to understand those graphs, we certainly used a lot of results from graph theory, and even those were not completely enough or completely applicable to our setting. So we had to improve them, but they are based on some basic lemmas that are due to Estrada. So I just wanted to say that here. Okay, in the refined class of this pair graph, it turns out that among them, the ones that will be effective for our equation to get to the equation, we call them ladder graphs. And they are the pieces that do not give 0 contribution at the limit. In fact, they are the ones that contribute to the relevant parts of the three-wave equation that I already wrote for you before. Okay, so the fact that like I mentioned already, in our case, the nonlinearity is quadratic makes the diagram much harder to analyze. I mean, you have to, in the sense that you have to go a little bit deeper. So it's kind of like having to study all the way to a sort of second order approximation. I mean, you have to go deeper in it. And this is, we have to do more than what is done in the analysis of Lucarin and Spon. Okay, so I wanted to at least give you an idea of what these graphs look like. So I'm going to talk a little bit about this picture here. So this is an example of the Fireman graph. And where does this come from? So when you have to examine a solution from a time t, and you use the Duhamel expansion, you keep replacing the functions themselves with the expansion that you had before. And so you walk backwards in time from t to 0, and we select this particular intermediate time, so S2, S1, S0 to 0. And the departure here comes from the fact, so we start with 2 because we have a quadratic nonlinearity. And then the departure here just tells you that you are replacing one function with the nonlinear part in there. So one function gets replaced by 2 because the nonlinearity is quadratic. And we keep track of where that happens, which time slice that happens. So here happens on S2. So on my frequency K2, 2 stays for the which stage the first 2 is the index that tells us at which time that happens. And then that splits into 2 because we are replacing a function with nonlinearity. And then of course this plus and minus stand there because you can replace with a function which is, here we are doing this argument at the level of the Fourier coefficient. So the Fourier coefficient could be the coefficient itself or could be the conjugate of it. So that's why the minus will stand for the, I can't remember now if it's the coefficient itself or its conjugate, but then the other one, the plus tells you that it's the conjugate of whatever you put in there. So this plus and minus tells you if you're conjugate or not. The case, the indices tells you how you split in respect to times or with respect to the frequency and so on. Okay, so I just wanted to give you a little bit of an idea how this Feynman diagram come in. Now, don't be scared about these slides. I just wanted to get one information out of this. And the information is that in the analysis of the Duhamel pieces, we're going to use cumulants. Now, it's not really important what obviously this brackets tells you you're taking an average, and it's not important to tell you exactly what these cumulants are. What I wanted to stress on these slides are 2 facts. The first fact is that you are looking at a certain average and you write it in terms of sub-averages by matching different indices, if you like. So you expand this big thing with sub-averages, let's call it that way. Another thing that I wanted to show you this because I'm gonna give you a picture of some more diagrams in which I wanted to connect the fact that you have this product here with a certain visual representation of that. Then another important fact that I wanted to take from these slides is the cumulant correlation functions. It's not important what this is represented by, you don't need to know that, but what is important is that you need to have a very good estimate for this cumulant correlation function. So these 2 information, the fact that when you have a big average, you split into smaller ones, and the fact that for the argument to work, you need to have a very good estimate for this cumulant correlation function. Okay, so let's concentrate on the cumulant correlation function, the MTN that I just mentioned before. So in our case, where does the estimate come from? At this, we go back to the density function rho and back to the equation of the density function rho. In fact, the good estimate is obtained by using the equation of the density function rho, and you get in a very explicit manner. So it's going to be a function g. It's not important for you what g is at the moment, but for us it's explicit. I wanted to note that in the work of Erdős, Solmhofer, and Yao, and Lukács and Spon, the same type of correlation function needs to be estimated. And in the first work of Erdős, Solomon, and Yao, that's done via lemma, they prove a lemma. While in the Lukács and Spon, that comes as an assumption. They make an assumption to estimate this M. Finally, what about the use of the cumulants? Well, here I have 2 pictures that I hope gives you an idea how I translate the formula for the cumulant into the representation of the graphs. So in the first graph, I underlined this dot here. This is a vertex for our graph. And when you look at the fact that you see this dot here, what you see is that what you are computing is just one expectation. So you just compute one integral. In this other graph, when you see these other 3 red dots, you look at it and you realize that what you're doing here is actually computing 3 different expectations, one for each dot. So that's the correlation between the cumulants formulas and at least one idea. It's much deeper than that, but just to give you a visual idea of how this cumulant translate into these graphs. One last thing that I wanted to mention, because I'm running out of time, is the following. So I mentioned several times that the cubic nonlinearity is much more amenable to our estimate than the quadratic that we have to deal with. And let me just say that one place where you see this is at the end, when you do all your integration and you're looking at your graph, you're left with 3 free vertices. And when you do that, because there are 3 free vertices, you're gonna just do a Holder inequality. You put each one of them, or whatever correspond to the function correspond to them in L3. L3 is a very good space. We have a good estimates in terms of lambda for that, and we're good. In the quadratic nonlinearity, if you try to do the same kind of argument, you will end up by doing Holder in L2. And L2 is not a good space to have decays with respect to lambda. So you have to be much more clever than that, and you're gonna have to regroup some of the verses in a very specific way. And okay, this graph here is not very meaningful for you, but I just wanted to say that if you were dealing with a cubic nonlinearity, you will just see these 3 graphs, there's 3 vertices here, and you will integrate each one of them separately, you'll be fine. Instead, in our case, we have to recombine them. So there is a grouping of the verses that needs to be more suitable in order to pass from an L2 standard estimate, which is not enough, to more an L3 estimate, which will give us an extra decay on lambda. And I'm going to stop here. Thank you.
Thank you. Thank you, Giuliola. Are there any questions?
Actually, I have a question. I am not. Just can you, maybe you already said it, but how do you define your cumulants in terms of the dynamics? I guess these are dynamical cumulants.
Yes.
Okay, there is this formula, but here my question is say, what do you mean with this?
They appear, I'm sure, Laura, you know much better than me this. So, but so the T here tells you that there is a dynamic, okay? So they appear in the Duhamel expansion. And there is also when you write them, there is also the density function rho, right? And then that one satisfies certain conditions from the equation that we had before. So that's where they appear. And
yeah, my question is more like, say, a graphical intuition of, so you have all these graphs, but say, how do you, so cumulants are related to clusters, and
yes.
And what is this clustering relation between the different guys?
So this is the graphs that in my mind explains that. So these are these dots that you see here is like, for example, in this particular graph, then what we are doing is it's kind of like if the product here that you have, this one is going to be just by these 3 pieces, given by these 3 pieces. So the way I see it, but Bin should intervene because he is the expert on this area. The way I see it is by how you match these vertices at the time when you go all the way backwards.
Okay, so the different relations that you have, so the different connection that you have between your particles are exactly. Either a connection at time 0,
Yes.
And you have a pairing at time 0,
Yes.
either a connection, say, in the dynamics, because you
Yes.
have this trilinear interaction.
Exactly, which is actually bilinear. Yeah, I mean, we have to match, you see, we have to match them in a right, like I say, it's more complicated when you have the bilinear interaction because you have to do the matching much better, much more subtle in a way. Beam, do you want to add something that it's more?
So when you have the dynamics, right? So when you take the expectation, you have the cumulants with respect to this density function of the dynamics, not at the initial condition. So basically, however, the beautifulness of the work of Fao is that you have this equation, and in some sense you can use his lemma to estimate those correlation function. So this is why you have, so in the case of Spawn, he has to put the system in the equilibrium so that he has an L1 clustering estimate. For here, this is by far we can have it using the density function, right? So, and the clustering is
you don't have even at equilibrium, you don't have an estimate of all cumulants.
Right. So this is an assumption by him, but in this case by Fao, so we use the density function, and so you can estimate that all of the L1 clustering using this density function. So
yeah, I guess. Yeah, Laura. So in these slides, this is where I said that the looker in a Spawn, they had to assume that you have bound for this M here, even if you are at the Gibbs measure, the equilibrium sign. So,
but because there is no in the theorem that they proved that there is no explicit assumption like this. So is it hidden in the fact that you have only a result for a very short time, or so? I don't remember.
So in his paper, he has an assumption like this. So he put the assumption in one of the first pages. So for us, I think using the idea of how we can do it.
Okay.
Yes, if I can, do you hear me if I speak like this?
Yes.
Maybe like this?
Yeah, we hear you well. Yeah.
Okay, no, just in my case, I work, it's a linearized, so these are fluctuations. So in this case, if you look at fluctuations, you have almost for free the propagation of chaos. But here you seem to say that there is some real nonlinear dynamics evolving. So I have a question: is what's the role of the noise? When does the noise play a role?
Yeah, is in the what I said before in the equation for the rho. Let me go back to it here. So this CR. So you see here you have the dissipation. It's in front of the derivative of order 2 with respect to the angle. So when CR is there, and this is a positive constant, you have a dissipation. So it plays a role in that sense.
But what is the scaling of CR?
CR is less than lambda. Okay, let me just go back here. So this is the way it is written. I'm sorry about the phone. I don't know why. Let me go here. So we write in terms of, to appear the CR correctly in the equation for rho, we write a square root of CR, and CR is less than lambda to the 2 minus epsilon r.